Yes, so thanks for the introduction, Rosa. It's really good to see all of you, and thank you for switching on your cameras. Who feels like doing that? So I feel like I have an audience to talk to. Today I'm going to talk about explosions in the sky. Let's see if my slides actually decide to advance. One sec. Oh, I need to switch it on. Yeah. I will start with a brief intro to overview where we expect stellar explosions to happen, and they are powered by black holes and neutron stars. These are cataclysmic events. And so let's look at where black holes live. So obviously, one place to find black holes is at the centers of galaxies. So these are quasars or active galactic nuclei. At the center of every respectable galaxy, there is a supermassive black hole with a mass of a few million to a few billion solar masses. The other kind of bucket in which we can classify black holes is a stellar mass black hole. Those range in masses between a few and a few tens of solar masses. So you can find them in binary systems where like a star, normal star, dumps its gas onto the black hole. And you can see this results in the formation of this whirlpool of gas, which we call the accretion disk. That then together with the black hole produces these collimated outflows, just like it does actually in the AGN. So these are called black hole binaries. It's a binary, a star and a black hole. There is also another system that is very exciting, gamma ray bursts, short gamma ray bursts, which happen as a result of a collision of two neutron stars. And as a result, you can either get a hypermassive neutron star or a black hole. You can also collide black holes with neutron stars, and you will get something presumably very similar. And finally, this is showing here the collapse of the core of a massive star once it exhausts its fuel. There is really no more thermal pressure to support the star against collapse. And so it falls onto itself, forming a compact object at the center, a black hole or a neutron star, surrounded by an accretion disk. Just as before, this results in the formation of these collimated outflows that we call jets. They drill through the star, emerge outwards. And if we happen to be looking down the barrel of a gun of this jet, we will see emission from this jet, which in the case of gamma ray bursts is in gamma rays. So you can think of these as gamma ray laser pointers, essentially, that pierce through the universe, come to us from high redshifts. And so gamma ray bursts are really exciting ways of looking back into the past. So far here, you see that there is a hole in the mass distribution. We think that there is an intermediate mass black hole class over here with masses ranging between a few hundred and a few 100,000 solar masses. These could be either the low mass end of the supermassive black hole distribution, or they could be high mass end of the stellar mass distribution. It's probably a combination of both. But what makes them exciting from the point of view of me, from the point of view of explosions, is that they could be the missing link in our understanding of where so-called ultraluminous X-ray sources come from, the ones that produce way too much X-ray emission for their mass, had they been stellar mass black holes. And I will come back to this in a moment. And you can see in all of these cases, the combination of accretion disk around the black hole, including this one, that's not shown, results in the formation of these collimated outflows or jets. These are the sorts of structures that I'm going to be focusing on during my talk. But just to be fair to non-black holes, you don't have to have an event horizon in order to produce the jets. In the case of neutron stars and white dwarfs and regular stars, you can produce the jets just fine. The jets are very resilient. And the basic physics behind the jets that we will get to in a moment is a spinning magnet immersed into the ambient medium. That's all we need. So a spinning neutron star or a white dwarf is a spinning magnet. Same thing about a star. And a black hole is also a spinning magnet, except it can't have its own magnetic field, so it has to be provided by the accretion. So that's the biggest difference. But by and large, the behavior of all of these types of systems is very, very similar on a qualitative level. So let's try and kind of review what sort of exciting things happened recently in this field. Of course, detections of gravitational waves from colliding black holes was a big deal, and I use Malevich's black square painting to illustrate that. I in fact claim that Malevich predicted the detection of gravitational waves. Why is that? Well, because he painted this, I think, in 1915, so right around when general relativity came out, and also he painted nothing, and we saw nothing. We only heard the ripples in space-time. So that's why I say he predicted gravitational waves. So typically these black holes that collide, they're very old, and there is really not much gas around. And so we don't really hope to see anything as a result of the merger. However, if we have collision of neutron stars, lots of neutrons in one place, that's a recipe for disaster. And so not only do we see gravitational waves, we also see the mushroom cloud and the glow of the mushroom cloud, the radioactive cloud that emerges as a result of outflows that are neutron rich, that then synthesize heavy nuclei that are radioactive, they decay, and it's the radioactive glow that we see as a kilonova, which is a window into nucleosynthesis, and perhaps opens up the opportunity for us to understand where all of the stuff that we live in and surrounded with came from. These core collapse objects are still mysterious. Some of them manage to last, instead of the typical maybe 10 to 100 seconds, which is what it takes for long gamma ray bursts to operate. Some of them last up to hours, 10,000 seconds. And not only do they do that, they also manage to explode the star in addition to producing the jets. How can you do both? How can magnetic fields manage to do both of these is an open question, because if you think of the jets as taking away the energy and relieving the pressure, magnetic pressure in the center of the star, then you need to fine tune things such that the star explodes and the jets are still there. It's like inflating a balloon with two holes in it. If you inflate too fast, the balloon will pop. If you inflate too slow, the balloon will deflate. So you have to inflate just right, such that not only do you have these jets survive for hours, you also will not pop the star too soon, and it won't deflate either. So how this works is a mystery. Let me move over to these ones. What we thought were intermediate mass black holes behind the ultraluminous X-ray sources turned out to be a couple of solar mass neutron stars. And we figured that out by noticing that there were pulsations, and therefore there was a surface, and therefore it couldn't be a black hole. And so these regular pulsations is what revealed to us the nature of the central object. So how do neutron stars manage to produce so much radiation for their tiny mass is an ongoing mystery, and a lot of people are working on that. Finally, the last but not the least, there is a really fantastic laboratory, which nature produces when a star comes too close to supermassive black hole. The tidal forces of the black hole overcome the forces of gravity that keep the star together and spaghettify it. It's actually a term. So you essentially stretch the star from a ball into a spaghetti strand. That spaghetti strand wraps around the black hole, collides with itself, and feeds the black hole. And not only does that create a bright flash, which can last for months to years, it can also produce jets. And that's spectacular because in these cases, we can see activity on a human timescale as opposed to on hundreds of millions of years, which is a typical timescale for quasars. And these systems produce the jets for us in addition to the accretion. So we can understand accretion for very well-controlled parameters for one solar mass being dumped in the black hole, and we know how much jet and how much luminosity was produced. Of course, things are not as simple. We would expect that all tidal disruption events look the same, but it turns out that you will be hard-pressed to find two of them that actually look the same. So I won't get into the details. Suffice it to say, numerical simulations is what can allow us to try and make headway in understanding what makes these, what we would think naively perfect laboratories, very reproducible, look so different, That will be the theme of my research that I'm going to share with you. How can we use numerical simulations to try and interpret the observations and solve observational mysteries? So before I go and show you some movies, let me try and pose some big questions. One question that I'm really interested in is to try and understand what makes it a healthy jet. So I will be playing the role of a sort of jet dietologist. So what sets the power of the jets? How does it compare to the accretion power? What causes the jets to collimate into this tiny opening angles of less than 10 degrees? What allows them to accelerate to Lorentz factors of hundreds, if not thousands, in gamma ray bursts? So that corresponds to the speed with which the jets propagate to be a really good fraction of the speed of light, like not 0.099, sorry, not 0.99 of the speed of light, but like 0.999 of the speed of light, something crazy, something that's really, really many nines after the dot. So how do they manage to get there? How do the jets pick up the mass that they carry? Because we know the jets shine, there has to be mass on them. Where do they get that? And finally, once you've gotten the mass, once you've gotten the emitting electrons and positrons, perhaps, what energizes them and causes them to emit? These are all open questions. Finally, if I have the time, I will try and review what happens if the accretion flow is tilted relative to the black hole. In that case, will we even get a jet? And if we will it shoot out perpendicular to the disk or to the disk midplane, or perpendicular to the black hole midplane? So these are all very important questions. We would like to know what determines the jet direction, and what does the jet direction tell us about the accretion system? Finally, we see that not all of the jets are stable. Some of them fall apart. So what happens to those poor souls? I will also try and discuss how much can we trust our simulations, because it's of course they're of course done at a finite resolution. And so if you increase the resolution more and more and more, will we get something that doesn't depend on the resolution, or perhaps it does? So this is a really important question that has been bothering the numerical astrophysics community for a while, and I will try and see if I can contribute a little bit to addressing it. So why would we want to study jets? Well, one of the most easiest way of selling that is the effects of the jets on the environment. And this is an example of the Perseus cluster, where you see that the central black hole hiding somewhere here inflates cavities, sends out shock waves, and this is a sharpened image where you can see a lot of action over here. So basically, supermassive black hole uses just to explode the galaxy. Similar thing is happening in the M87 galaxy, where you see the cavities inflated by the jets, there are shocks, and the jets themselves. And finally, this is perhaps the most dramatic example of jet feedback, where blue color shows X-ray emission and purple color shows the radio emission. And so you see that where there is purple emission, there is no X-ray emission. It's suppressed there. So it means that what we've gotten here is these jets, the inflated cavities that displace the thermal emitting X-ray emitting gas. And so it means that the jets had to have performed work on the environment. It means that the jets must carry a substantial amount of energy. And if we compute PDV work to inflate these cavities and compare it to the entire rotational energy of the black hole, if it were rotating at the maximum spin, we will find that the two are comparable. So whatever process makes the jets, it's extremely efficient at extracting black hole rotational energy. It's as if we came with a stick, stuck the stick into the black hole, took all the energy away, and dumped it into the ambient medium. So spoiler alert, I will argue that it is the magnetic fields that are responsible for this fascinating process. So let's try and look quantitatively at this process. Sorry. Let's plot the mass of the black hole versus the velocity dispersion for a bunch of galaxies. So every dot is one galaxy. And what we're going to find is that there is a very tight correlation between the two. The central supermassive black hole mass knows about the stars and the speed with which the stars bounce around in the galactic bulge, although this galactic bulge is so far away it doesn't feel the black hole mass. So there is no direct way of talking for the black hole to the galaxy. So through gravity. So it means that there has to be another way for the black hole to talk to the surroundings. Could it be through jet feedback or radiative feedback? Or perhaps maybe galaxies and black holes, they evolve at the same time, and that's how they know about each other. So this is still an open question. Another way of looking at this the black hole feedback is to plot the radial luminosity of a bunch of galaxies versus the optical light from the center, or nuclear B-band luminosity, in a log-log plot. And you see that there are two tracks that the galaxies follow. There is a top radio loud track and the bottom radio quiet track. So for the same optical light, which we think tracks the mass accretion rate, we can have either a lot of radio emission or very little radio emission. And the difference between these two tracks is 3 orders of magnitude in radioluminosity. So in addition to the mass of the black hole, which is within a factor of 10 between these two tracks, and the mass accretion rate, which is presumably the same for the same value of the abscissa, we are going to have another parameter or a bunch of parameters that tell our black hole whether it should land on the top or the bottom track. So what is that parameter? Is it a magnetic flux? Is it an ambient medium? Or is it black hole spin? For magnetic flux, if we have strong magnetic flux, then maybe there will be stronger jet and more radio emission, and so it will land on the radio loud track. If it is ambient medium, perhaps if we have more ambient medium, that will cause more interaction and we will see more radio emission, maybe. Or if this is a black hole spin, perhaps the black holes in the top track rotate faster than the ones in the bottom track, and that's what causes the difference. It could also be a combination of these parameters, or it could be none of these, because as you see, there are different symbols that are showing different parts of these tracks. So it's possible this is just a selection effect. And so if we were not looking at these particular surveys, but if we looked at all black holes somehow, then it would be continuous distribution. So this is still an open question, and I feel like I'm getting a bit frustrated. I'm not getting any closer to the answer of how black holes are producing feedback on the galaxy. So let's take a look at images. Perhaps images will help us to guide our intuition. So these are two of my favorite galaxies with jets. This is a Cygnus A galaxy, and you can see it's a really well-defined collimated jet that ends up in a puff. So this is a hot spot where the jet slams into the ambient medium, and then it flows back. It's similar to a garden hose that you directed at the wall. The water hits the wall and bounces back. That's precisely what's happening over here. The M87 galaxy is different. First of all, you see that the jet is kind of wiggly and falling apart. There are different blobs that you can tell in this jet. And then eventually it does fall apart, ending up in the sort of swoosh. And the swoosh actually outruns the jet as opposed to flowing back. It actually is ahead of the jet. So how does it work is an open question. And you can see that there is this big difference in morphology. In fact, this is known as FR1, FR2 dichotomy. And this has been an open problem. What causes dichotomy for the past 45 years? Yeah.
And how similar are the sizes? How similar are the sizes between these two jets?
Yeah, so this is around 70 kiloparsecs, and this is around 5 kiloparsecs. So this is a very long jet that makes it out of the galaxy. This one dies well within the galaxy. And really good question. Thank you, Diego. It's super important for us to know what causes one of the jets to fall apart inside the galaxy, and therefore create destruction within the galaxy, because it dumps all of its energy into the galaxy, as opposed to punching a hole and getting out, meaning that it evacuates the jet evacuates the energy of the black hole to the safe distances where it won't do any harm to the galaxy. And so understanding when we get one or the other is really, really important. Any other questions? So so far we haven't been doing so great. So hopefully maybe, oh, and by the way, you see that there is only one jet. The other one we don't see because it's pointing away from us, and because of the relativistic beaming, the jet tends to shine in its own direction because of relativistic motion. It's the aliens on the other side of the black hole that will see a bright jet, but they won't see our jet. And at the end, once it slows down and relativistic motion subsides, you see that there is a swoosh that is similar to the one on this side. So we think that both jets are pretty symmetric. It's just we don't really get to see the other jet in this case. M87 is a very special. Go ahead.
I do have a similar question to Diego's. So if you were to also plot here the axis, which direction would they be in both of them?
Sorry, I didn't quite hear. If I were to plot also what?
The disk
the disk of the galaxy. Typically perpendicular to the jet. So in these cases, they're perpendicular. In both cases, yeah. But it doesn't have to be. I mean, why would it have to be? Or maybe it has to be. So this is an open question, I would say. And we know in some galaxies that there are relics. There are these X-shaped galaxies where you have jets that are fresh, going in one direction. There are jets that are old or going in another direction. So we know that the jets don't have to go out perpendicular to the galaxy. Something else might control their direction. And some people say, oh, maybe it's black hole spin. What I will argue, it is the direction of the angular momentum of the accretion disk that controls the jet direction in which they go, which is much easier to change than the black hole spin. Black hole is huge, whereas the disk is tiny compared to the black hole. It's connected galaxies. And so if the black hole eats a star or a molecular cloud or whatever, with a different orientation of angular momentum, you will get a jet that goes in a different direction. We will get to that in just a moment. Thank you very much. Excellent question. So what if we zoom into the very center? Then you see that there is a black hole. This is now 1 light year instead of 3,000 light years. So we've zoomed in by a factor of 3,000. And this is 1,000 black hole radii. So we are getting close to the black hole. And you can see that there is a pattern moving away from the black hole. So what we think is going on, the jets form at the very vicinity of black hole event horizon. And as they move away, they accelerate. And eventually by these distances, they reach relativistic velocities, like Lorentz factor in the case of 97 of about 6. So this is why we only see one jet. The other jet is moving, also presumably at Lorentz factor of 6, moving away from us. And that's why its emission is beamed away from us and we don't get to see it. Oh, actually, I'm showing these distances, 70 and then 5 kiloparsec. How could we try and zoom in even further? And so in order to do that, at least at the radio frequencies, we would need, in order to satisfy the diffraction limit, lambda over d is the smallest angular scale that you can resolve. D is the size of the telescope and lambda is the observational wavelength. We would have to make a telescope the size of the Earth. So that's the size that we need in order to resolve the length scales comparable to the black hole event horizon. Of course, that's ridiculous. We'll never be able to do that. But we don't have to build a telescope the size of the Earth in order to get that small angular resolution. What we can do instead is scatter telescopes throughout the globe, put them together as an interferometer to correlate their signal. And when we do that, then we can fill in the phase space or Fourier space of the image, because radio telescopes, they see things in Fourier space. So you can see these tracks that each pair of telescopes tracks on the sky as the Earth rotates underneath the sky. And the more telescopes you add to your array, the more tracks there are, the more data you have in this so-called UV Fourier plane, and the higher quality image you can get by computing the inverse Fourier transform of this plane, which is a whole industry in radio astronomy. So if you get a really good observation, actually a really good simulation, this is a very advanced code called Interstellar that produced this, you can get something really cool. But indeed, a couple of years ago, we've gotten the results of the Event Horizon Telescope, the first data release. And this is the zoom in onto the very, very central region, which is just about 10 gravitational radii in size. What we're seeing here is the black hole. This is the place where all of the rays of light are absorbed by the black hole. And this is the Einstein ring that's kind of lensing produced by the black hole. And you can see how it changes from day to day. There were 4 days during which the observations were taken. You can learn a lot of interesting things from here. First of all, from the size of the image, you can directly read off the mass of the black hole. The bigger the mass, the bigger is the Einstein ring. And so from measuring the size, you can immediately convert it into the mass. So it's 6.5 billion solar masses. There was a controversy whether it was 6 or 3 billion solar masses. Now we know for sure that it is 6 billion solar masses. That's important. The other thing is you can see that the bottom of the image is brighter than the top. It means that the rotation and accretion disk around the black hole is coming towards us at the bottom and away from us at the top. In fact, because rotation near the black hole is controlled by the space-time dragging of the black hole itself, what we're seeing here is really the rotation of the black hole, not the disk. So even if we change the direction of the disk, the pattern, bright, dull, will not change. So, and if we assume that the rotation of the black hole is happening perpendicular to this large-scale jet, whose direction I'm showing over here, it means that we should have something that rotates like that. So it means that the black hole needs to be rotating clockwise on the sky, which is amazing. Just from this observation, we now know, we don't know how fast the black hole is spinning, but we can tell which way it is rotating, which is totally fascinating, at least for me.
Do you have any constraints on the spin?
Do we have any constraints on the spin? It's very hard to place constraints on the spin. The most robust constraint on the spin comes from the fact that we have a powerful jet. So there's got to be some spin involved. So typically people say, oh, spin has to be greater than 1/2. I mean, is it 1/2? Which is kind of a typical spin where the jets are kind of lively and then strong and powerful, but it could be 0.3, it could be 0.7, 0.9. We don't actually know. I would say that right now it's really hard to tell. The jet power scale is roughly a spin squared. And it seems from what we can tell that the jet power is comparable to accretion power within a factor of few, which means that, and it's very hard to get there. If you max out the spin, max out the magnetic fields, you get to basically roughly equality between the jet power and accretion power. And the spin controls the jet power roughly as a squared times m dot c squared. So that's the jet power. So if you go to spin of 1/2, it means you've reduced your jet power by a factor of 4. If you go to a spin of 1/4, you've reduced your jet power by a factor of 16. So probably it's not 1/4, because otherwise you would not be able to produce the jet as strong. And of course, we rely on theoretical insight of how jet power connects to accretion power. So that's why people think that's probably of order of 1/2 or higher. All right, that's kind of the idea. It certainly cannot be 1/4. That would be too small of a spin in order to produce such a powerful jet we observe. So that's the strongest constraint on the spin as far as I know. Not from the images. It seems like the images are pretty degenerate. More recently, just in the last couple of weeks, new results came out with polarization of the image. And the polarization indicates that the geometry of the magnetic field is poloidal. So it's not toroidal, it is actually poloidal, so perpendicular to the disk. And that suggests that there is large-scale magnetic flux that dominates the whole evolution. And so what we think this tells us is that there is dynamically important magnetic field at the center, which we kind of could have guessed because jet power was comparable to accretion power, which already told us about that. But now we have an independent indication of the same. So everything points towards magnetic field being as strong as possible. Lots of vertical magnetic flux accumulated at the black hole produces the jet as strong as possible, basically. So magnetic flux is at the maximum and the spin probably pretty high. As I said, probably 1/2 or greater. Any other questions? Okay, so let me move on to the theory. How do jets get made? Let me check what the time is here. Okay, so so let's not worry about the nature of the central object. Could be a neutron star, a black hole, or a regular star. What matters, as we discussed at the beginning, is that it's a spinning magnet. So there has to be a magnetic field line that's sticking out of the central source. For simplicity of argument, I will attach the other end of this field line to a seeding, which represents ambient medium. In the galaxy, that's the ISM. In the core collapse, it could be a star, and so on. We will remove the seeding in just a moment. So let's flick our fingers and let's spin the central object. After n rotation of the central object, the initially vertical magnetic field line, this one, will develop n loops. Every rotation will wind up the vertical field line and create an extra loop. So if we have a loop, it means that we have toroidal field. So the more loops we get, the longer we wait, the stronger will be the toroidal pressure of the magnetic field. And eventually the sealing will give in. The jet will push through, or you can think of it as a drill. You know, we've twisted the magnetic spring by the rotation at the bottom, and the spring eventually expanded or drilled through the ambient medium. And so now what we have is we have basically a magnetic spring that's expanding under its own pressure. That is basically what the jet is. You create new segments of the spring, which push out the old segments, and that's how the jet kind of sustains itself. You can think of the jets maybe a slightly different picture where we still have these original magnetic field lines, kind of a catalyst of the whole picture. You do have to have these vertical magnetic fields because the rotation converts this vertical field into toroidal loops, and these loops slide upwards along the magnetic field lines, these vertical magnetic field lines. As they do so, they expand, the pressure drops, and the pressure gradient pushes them out and accelerates them. So that's how jets accelerate. That's how they propagate. And the power is carried by the toroidal field, by the Poynting flux associated with this moving hoops of the toroidal magnetic field.
Sorry.
So
Sorry,
we can actually verify. Go ahead.
So I'm confused.
No,
So
go ahead.
wouldn't we have expected in the M87 polarization as the footprint? So like to see this colloidal magnetic field around the jet and not the vertical magnetic field? I don't know.
The emission is happening very, very close to the black hole. So it's not the jet that's emitting. It's really the stuff that is within innermost, few gravitational radii of the black hole, like 10 maybe. And it drops precipitously towards larger distances. The emission is probably concentrated in the equatorial plane as well. So if you take a simulation where you have strong magnetic field, and if you take a simulation where you have weak magnetic field, and you try to make a synthetic image, you will find that the one that gives a better match is when you have strong poloidal magnetic field, and you get this regular polarization structure that looks just right. If you start with a weak poloidal magnetic field, you won't get this. It will be more disordered, and I think the direction of polarization will also not be correct. Okay. So that's what allows us to tell what is the shape of the magnetic field, its orientation, and presumably strength as well. Because if you have a regular large-scale poloidal magnetic field, it means that it's dominating dynamics. Otherwise, it would be all turbulent. It probably wouldn't be there intact and creating this large-scale polarization structure.
Okay, thanks.
So just
sure.
By ignorance, Gloria.
Yeah, no, go ahead.
In the figure you have with the magnetic field and the loops, what happens perpendicular to the polar region? So do you not expect to get any magnetic fields, let's say, frozen in to the accretion disk somehow, or?
So you're asking where is the accretion disk in this picture?
Well, I'm asking what happens to the magnetic field perpendicular, associated with that could be associated with the accretion disk.
Yeah, I conveniently left it out. Right. Thank you, Gloria. Excellent question. So accretion disk is around here. The role of the accretion disk is to hold the jet from the sides. In fact, it's the pressure of the accretion disk that controls how fast the jet can expand, and so therefore how fast it collimates or the shape of the jet. The disk supplies the magnetic field to the black hole. Black hole gobbles it up and then winds it up and produces the jet. So that's kind of how the disk and the black hole talk to each other in terms of the magnetic field. Let me see. Do I show a picture of this later? Yeah, I think I will show you a video where you might be able to glean how the jet and the disk kind of coexist later. I I have recently I started showing almost exclusively 3D movies, but I think I still have a couple of two-dimensional vertical slices where you will see both the disk and the jet, and you will see how the two relate to each other. So just bear with me for maybe 5 more slides and I will get there. Does that sound good?
Yeah, I guess the question I had was, is there no magnetic field within the disk?
Oh, yes, there is. Yeah, because all the magnetic field that the black hole gets came from the disk. If you were to remove the disk, this magnetic field will not stay on the black hole. You will get a magnetic explosion because you have a lot of energy here, no energy outside. So magnetic fields will just explode because pressure here and no pressure there means that there are pressure gradients that will push everything away. So everything will fly apart. So you have to have stuff that holds this magnetic pressure in place. So there has to be stuff that is as pressurized as inside the interior of the jet. And that is the pressurization that the disk provides, and its winds and outflows. Does that answer your question, Gloria?
We can get back to this at the end. Sorry for the interruption.
Perfect.
You.
Okay, sounds good. No worries. Yep. Great. Cool. So how do these jets look like? How do we know how fast they move? And so you can do this by actually tracking the features in the jets. So this is a series of images of M87 jet. This is a zoom in of that region. So that's the total jet in the optical. And this is like the box that we zoom in on. And you see from 1994 to 1998, every year there is a snapshot. And you see that this blob tends to move away from the kind of the center. And the same thing you can tell for a few other ones. And the speeds are pretty consistent. They all are around 6 times the speed of light. So that is weird. How can anything move faster than the speed of light? Of course, nothing really moves physically at that speed, superluminal speed. It's just an illusion because the emitter is catching up with the light itself because it moves so close to the speed of light that it actually appears to move superluminally on the sky. So this tells us that the Lorentz factor of these blobs is around 6 or more. It turns out that this degree of superluminal motion directly translates into lower limit on Lorentz factor. So 6 or greater. There is another thing that we can glean from these images, that is how the radius of the jet, cross-sectional radius, changes as a function of distance along the jet. And so this is 1, 10, 100, 10 to the 6. And this is 1, 10, 100, 10 to the 8 on the side. So, and this is on a log scale, and the measurement unit is the gravitational radius of the black hole, basically the size of the black hole. And you can see that for maybe 5.5 orders of magnitude between the black hole and the sphere of influence of the black hole, which is the Bondi radius right here, around 10 to the power 5.5 gravitational radii, we see that the jet maintains a very near parabolic shape. So z goes as r, so z is the distance along the jet, r is the cross-sectional radius, to the power of 1.7. Not quite a parabola, which would be r squared, but parabolic-like shape, parallel shape. So how come nature knows that it needs to create a perfect power law that extends for 5.5 orders of magnitude? That's ridiculous. How can everything come together into this perfect harmony of a single power law? And that's something that we decided to check. So I'm going to be investigating how the jets could be produced in this 2-dimensional space. On the x-axis, I'm going to be plotting the strength of the vertical field. So strong vertical B field is on the right, weak on the left, and along the vertical axis is the thickness of the disk. So thick disks are at the top and thin disks are at the bottom. The easiest place for jet production is in the top right of this figure. That's because thick disks have an easier time holding onto the magnetic flux and bringing it to the black hole. If we go to the left, there is no vertical flux, so we expect no jets or very wimpy jets. And if we go down, then the disk becomes so thin. Like, think about thick disk as a book, and you try to cut through with a cheese cutter through the book, you will have trouble because it's thick. Whereas for a single sheet of paper, you can cut through the single sheet of paper no problem. Of course, this is a simplified picture. In reality, the disk is not a book and magnetic fields are not a cheese cutter, but analogy actually has some good intuition. Magnetic field has an easier time reconnecting through a thinner structure. And so it's possible that theoretically, we think that thin disks have a hard time holding onto its magnetic field. A magnetic field can reconnect faster than the disk can bring it in. And so that's why we think that this is the win for the jets and everything else is the loss. Of course, the truth is much more complicated. Let's get to that. First of all, as announced, we're going to try and check what is the shape of the jet and its acceleration. So this is a accretion disk. There is a black hole at the center, and there are these two jets. This is work led by a graduate student, now postdoc at Harvard, Kaushik Chatterjee, that I commented alongside Sarah Markov. And you can see that this is a very respectable dynamical range. You can't really tell that there is a disk in the black hole, but this is only 3 orders of magnitude separation, scale separation between the tip of the jet and the black hole gravitational radius. In reality, what we want is scale separation of 5 orders of magnitude. And that's what Kaushik managed to do. This is the cross-sectional radius versus distance. The dots are the observational points, and the solid curve is actually the shape of the jet. So without any tuning, we just took a big torus, donut of gas, put it around the black hole, flicked our fingers, pressed enter, the simulation ran. And what we found is that the shape of the jet seems to follow the observation data points just fine. And it follows a single power law. So single power law is actually a natural outcome of the systems. Now looking back, perhaps we shouldn't have been surprised so much as we were. That's because if you have a disk without any scale, like the disk is really big, then what would break the power law? It has to be a power law. So that's what we think is happening here. If you have a big enough disk, like we think M87 has, then you will have a power law far away from the black hole and far away from the Bondi radius, because these are the two scales that care in between. There is no scale, and so that's why we get a power law. In the bottom panel, we plot the Lorentz factor. So this wiggly curve is the simulation result, and the sort of broken power law is observationally inferred Lorentz factor. And you see that theory and observation seem to, or simulation observation seem to agree pretty well. What's really thrilling is that sometimes the jets accelerate, sometimes they slow down, sometimes there are spikes of Lorentz factor. So maybe now we get into the fidelity of simulations that actually maybe is telling us about the detailed structure of these jets, where there could be slowdowns, there could be speed ups, there could be blow ups in the jets, definitely something very exciting. At these really high resolutions that Kaushik was able to achieve, we start seeing a mixing of gas into the jet, something I will not have the time to talk about, but surface instabilities definitely can bring the gas from the outside to the inside of the jets. So what we've gotten here is the top right part of this parameter space, where we expected the strong jets to live, indeed contains strong jets. Well, let's try and the next simplest thing. Let's move to the left over here, where we don't have any vertical field, where we have just azimuthal field. Here, for sure, because there is no vertical magnetic field, there's got to be no jets. All right, let's do this.
Sorry.
So this is, yeah, go ahead.
Yeah, sorry, just I have a question regarding the previous simulation that you were showing. So I'm curious, what is the ambient gas? How are you initializing the space surrounding your disk?
Yeah, so thank you for this question, Emilio.
Okay.
Yeah, so what we do here is we take a black hole, put a donut of gas around it, and that's all that we do. We let everything else take care of itself. This is not the only way of initializing these simulations. You can do multiple other things. You can immerse black hole into uniform ambient medium and watch it accrete the gas from the edge of the sphere of influence. We're now running the simulations of that kind. They are more expensive. It's more complicated to bring the gas from large distances to small distances. So a more typical setup is when you start with the gas stores right there near the black hole. We kind of bring the gas reservoir in by hand, and we let it develop turbulence, feed the black hole, and produce the jets. That's what is typically done. So the simulation that I'm showing you over here is of the same kind. We have a black hole at the center and a power law distribution of gas. So density drops as a power law. This looks like a weird thing, but it actually is a torus. So if I were to zoom out, it would look like this. So a black hole is at the center, and then it's a finite size, a torus of a finite size, maybe 50 gravitational radii is the radial extent of this torus. And so what else we do?
Whether the shape that you were showing, this power law, does it depend on your atmosphere or your ambient gas? Because if in the previous case you didn't really initialize it, then I guess if you just take a denser gas, then maybe it is narrower, or don't know.
It's quite possible. We have not investigated that. I mean, we did. So the shape of the jets and the opening angle does depend on how extended and how thick the disk is. And so the fact that the first thing we tried, and it wasn't this disk, it was something else. The first thing that we tried and ran it, and it agreed perfectly with the shape, just suggests to us this is a generic structure. These disk solutions, they are perhaps, the thickness is not by accident, probably. If you were to form this disk self-consistently, which is what we hope to do by setting up uniform density at the edge of the black hole sphere of influence, let it fall in and form the disk self-consistently, those simulations will be much better. The cool thing, in terms of self-consistent determining the shape of the jet, the cool thing is that we get something that is basically essentially the same. So you would think that you may have thought that these sort of tori as initial conditions are a bit artificial, and that's definitely a worry. But we find that what we get with this tori is very, very similar to a more natural initial condition, where you just start with uniform gas, black hole somewhere in the middle, and then you add some rotation to this gas, let it fall in, form an accretion disk self-consistently. And that results in jets, I will show you, results in jets that are extremely similar in terms of shape, acceleration, power, to the ones that we get from this more artificial and simple setup.
Excellent, thank you.
Cool, sure. Thank you very much, Emilia, for the question. So here you don't see any lines, black lines, which you will see in a second. It's because I will show magnetic fields in this plane with black lines. That's because we don't see any initially. It's because we start with a purely toroidal field to begin with. So 0 BZ flux means that all the field is like that. There is no field that is like this. The right panel is a zoom out on the left panel. So this is 100 gravitational radii. This is 1,000 gravitational radii. So this scale is 10 times smaller, larger than this scale. So let's run the simulation and see what happens. At first, there were no magnetic field lines in the vertical plane, but now there are. And you can see that the magnetic field grows in size to the point of the magnetic field loops becoming so big near the black hole that although we started with no vertical magnetic flux, we ended up with a lot of vertical magnetic flux, and the size or the scale of these loops that are generated in the disk much exceeds the scale of the black hole, which means now we have a black hole that's faced with large scale magnetic flux. It's as if we started with vertical magnetic flux. So it's remarkable. Even when we start without any vertical magnetic flux, we still get it, and we still get the jets. In fact, the jets become as strong as possible. If we were to plot the power of the jets in units of accretion rate as a function of time, there is a gap in the data where supercomputers very helpfully purge the data if you haven't accessed it in a few weeks. And so that is where we lost the data. But luckily, the most interesting things are here and there. So here is how we build up the magnetic flux in the jets. Then there is this gap, probably nothing interesting happens there anyway. And then at the end, we end up with jet power that is around 150% of the accretion power. That is a telltale sign of dynamically important magnetic fields. In fact, if we start with as much vertical magnetic flux as the black hole would take, we would end up with precisely the same power, 150% of accretion rate. So that is indicating that we have reached the magnetically arrested disk, where the magnetic field is as strong as gravity, and the jet power is as strong as the accretion power. So surprise, surprise, start without any vertical magnetic field, and we still get it. So it seems like there is no way to try and kill the jets. And so it's a very important question here to try and understand how exactly does the vertical magnetic flux get made here. And this is something that undergraduate student Freddie and master student Audrey are working on. So you will tell me, okay, well, maybe these magnetic, maybe this, oh, and so by the way, this is the first time that these large-scale colloidal magnetic flux generation happen. We think that that's because we're the first who actually went to high enough resolution for a disk of a given thickness. So if you go to any lower resolution than this, you're not going to get this effect. The reason for this is once the turbulence generates vertical magnetic flux, the resolution should be strong enough to high enough to resolve the turbulent length scale associated with that magnetic field, the MRI wavelength associated with that field for the experts. If you don't, then the whole system doesn't self-sustain and the magnetic field decays. So you will tell me, well, it's high, but what if we double this or quadruple this resolution? Maybe everything will change. So this is something that we decided to test. This simulation now has even higher resolution, 5500 times 2500 times 2500. So this is like how many times? 4 times higher resolution than before. Just to set it in context, these resolutions are ridiculous. Typical resolution, state-of-the-art resolutions in our field is maybe the largest ones are 500 times 250 times 250. Whereas here we are 10 times larger in resolution in each of the dimensions, which is completely crazy and insane. Let me just show you what you get when you go to these higher resolutions. So the left panel is the density, and the right panel is the magnetization of plasma beta, the ratio of gas to magnetic pressure on a log scale. And you can see that there is a remarkable amount of detail that we get. And what's even more fascinating is that this current sheet that separates one jet from the other with opposite polarity magnetic fields, it coming out and coming back in. You see that there are these blobs that appear. And these are not just some blobs, these are plasmoids. And they only appear once you have resolved a magnetic reconnecting layer with enough resolution. I will not go into the detail, but this was shown in regular MHD simulations where you just take the reconnecting layer, keep increasing the resolution. And once you go through critical value resolution, it starts falling apart in this plasmoid dominated regime kicks in. And so this, for the first time, these really insane resolution and global accretion simulations allowed us to get to this plasmoid dominated regime. And why it's so important is once you get into this regime, no matter how much higher you take the resolution, you will not change the reconnection rate. The reconnection rate in plasmoid dominated regime is set by the physics of reconnection, not by the resolution. So that's really exciting. We might be finally approaching a well-resolved accretion state. So definitely much more work to be done, but this is definitely a very important step. And this work is led by Bart Ruperta.
What's the radius?
So far we have,
you have like a transition from a thick to a thin disk. So what's the radius at which is where you're getting these plasmoids?
So this is highly transient. So this is basically within the innermost 10, 20 gravitational radii. In fact, when we went to really high resolution, we found that basically what happens when you flood the black hole with magnetic fields. Once the magnetic field becomes too strong, it just pushes the disk out. And typically we thought maybe it pushes the disk out maybe to 5, maybe to 10 gravitational radii. But once we got to really high resolution, such as this one, we found it can push the disk out all the way to 20 gravitational radii. So that is one surprise that we got from these really high resolution simulations. So you can have a lot of violent behavior on these pretty large scales. So if M87 is indeed a MAD, indeed a magnetically dominated flow, then we might expect some variability on rather short timescales. We can talk about this. It would be really exciting to try and see if those are actually observed. So far, we haven't been successful at killing the jets. And actually, I'm running out of time. So what should I do? I can try and show you some tilted disks, or I can just wrap it up over here.
Oh, go ahead, please.
How many more minutes do I have? Because I can adjust the rest of the talk according to the time limit, because I know you have to go.
Oh, no, don't worry for that. we have a
We
lot of time.
typically-
Yes, don't worry.
We typically stay until 2 p.m.
Oh,
but
So
Cool.
half an hour more.
Yes.
awesome. All right. Well, that makes my life so easy. Great. Well, I'm so enjoying this meeting because you are asking me amazing questions. Please keep them coming. It's really a blast. So thank you. So then let me try and wrap it up in the next 15 minutes. So we have 15 minutes for discussion, if that's okay. Sounds good? Okay, awesome. Great. So what if we were to tilt the whole system, right? I think Diego asked me initially, I forget exactly who, what happens if the disk is tilted? And will there be a jet at all? That's a really important question. So let's try and look at this upper right part of the diagram and try and understand what happens. So why would we consider a disk tilt in the first place? Well, if we look at this image of the galaxy cluster MS0735.6, we will see that there is no obvious symmetry. So why in the world would we ever think that this is the right picture? The accretion disk is in the equatorial plane of the black hole, and outflows are perpendicular to that plane. Sorry?
Someone has their mic on, don't worry.
So, oh, I see.
I'll turn it off.
No worries. Yeah, so much more likely is the following scenario. The disk is tilted by some random angle, and if the angle is completely random, the typical inclination angle will be 60 degrees. And then what happens to these outflows and jets? Do they continue going along the black hole spin direction, or will they turn around together with the accretion disk? We don't know. We don't even know if the jets will be there in the first place. So let us look at the theory of what we expect to happen to a tilted accretion disk. If the disk is thick, black hole space dragging will cause the disk to be dragged around the black hole and precess. That's what we expect for thick disks. For thin disks, we expect something cool. The inner parts of the disk, we expect them to flatten out in the equatorial plane of the black hole and transition smoothly to the inclination at which the disk is fed, or rather the tilt at which the disk is fed. This is called Barden-Peterson effect. And since 1975, not a single general relativistic simulation with magnetic fields, which generate the turbulence and angular momentum transport, none of them has shown this effect. Does it mean this effect doesn't exist? Oh, we still haven't quite figured out how it works. And the challenge here is really big. It's the dynamical range, just as always. If we consider thin disks, and this effect happens in thin disks, the cost of simulation scales as the aspect ratio of the disk to the -5th power. So if we consider this that is twice as thin, we will have to spend 2 to the power of 5 more time, that is 32 more time computationally to simulate it. I can go into where this comes from, but just trust me on this for now, which is precisely why no one has been able to go to thin enough disks to see this effect, as it turns out. So how could we possibly make it happen? And the way to do that is to harness the power of new hardware architectures and combine it with the power of really awesome codes. So these are the people who have contributed to the development of the Hammer code. Matthew Lishka and Kaushik Chatterjee were at the origin of this code, and Valeria Rojosa is an amazing undergrad student at Northwestern. She's actually first-year undergrad, and she already made this plot of convergence tests for the code. So I'm just blown away. So it's just been a pleasure to involve all of the junior people, like students, and see how they pick it up and make it work. So what is special about this code? Well, it runs on GPUs and graphics cards instead of the CPUs, the central processing units. And the difference between CPU and GPU is like the difference between a Ferrari and a flock of horses. Ferrari has 400 horsepower. It's a really powerful CPU. But if you want to move apartments, there is not much you can fit on the Ferrari. Yes, it can drive your couch really fast from point A to point B, but you'll have to make a lot of trips. So that's the CPU. Horses, you know, if you have 400 horses, well, as long as you can break down your apartment into pieces, one piece attached to the horse, you can move your part in one go. And so if your algorithm is parallelizable for each horse or for the GPU, which consists of threads, if you can break down your algorithm into little bite-sized pieces for each thread to chew on, you can do magic. And that's precisely what we have done. Additionally, we've added adaptive mesh refinement so that the resolution follows the gas. So if you have a thin part of the gas, like small structure, then the blocks will be refined to provide the resolution where it's needed. And really important feature is not only are the blocks getting refined in space, they're also getting refined in time. So time scale, time step in these smaller blocks is smaller than the time step in bigger blocks. And also the blocks, this is a angle and this is distance. So this is 1,000 times smaller distance than that. And so the time step here will be 1,000 times smaller than that, which means we can extend our simulation domain as far as we want, and it won't cost us a thing because the time step out there is essentially infinity compared to the time step over here, which means that the cost over there is infinity times less than over here, goes 1 over radius essentially. So that's amazing, which means that we can simulate really large scale systems and perhaps bridge the divide, bridge the scale separation between the little black hole and the galaxy. And because we are the only game in town on GPUs and black holes, we get a lot of computational time, which is what allows us to do all of these cool things. So this is a tilted disk by 45 degrees, and the thickness that we consider here is still pretty thick, 0.1. It's thinnish, but not quite thin. Thin will be a few times less than that. The jets are shown in red, and the disk is shown in blue. So you can see that our theoretical expectations actually bear out. The disk is precessing because the black hole is dragging it around, and the jets are following the disk, not the black hole. So the jets are precessing as well. So tilted disks produce jets perpendicular to the disks. And if you see a precessing jet, it tells you about the precession of the disk and about the strong field gravity of the black hole that causes this precession in the first place. It's really cool. You show me precessing jet, I will tell you about the strong field gravity, perhaps black hole spin, perhaps the disk size, perhaps both, if I'm lucky. There could be ridiculous, you can take it to the ridiculous. You can consider a disk tilt of 90 degrees, where you would expect perhaps for there to be no jet at all. But this is an example of a simulation carried out by Kaushik Chatterjee. There is still a jet over there. We're still trying to digest what exactly is happening here, which way the jet points. But there is definitely a jet, and it's definitely a lot of fun. We can also try and make images of these tilted systems and see if the disk tilt could be reconciled with observations of, for instance, M87 on the event horizon. And so here we have two constraints. One is the image, and the other one is large-scale jet direction. And so what we would like for our simulation, whether it's tilted or not, to reproduce both large-scale jet direction and also the image on the event horizon scale. And so we can have a synthetic image over here of an aligned disk and of a misaligned disk. And you see that both of them agree pretty well with the observation. But when you tilt the disk, the maximum shifts a little bit to the left. And maybe we see signs of that in the image over here. So we definitely don't have the resolving power right now to tell these two apart, but in the future, maybe perhaps with the next generation of HT, we'll be able to get much more quality data, and perhaps we'll be able to start figuring out constraints on these new parameters, such as the disk tilt. So let's try and see what is left for us to explore. So here we definitely produce the jets. What about here, the bottom right? So here is a thinner disk, a factor of 3 thinner. The aspect ratio is 0.03. The disk is tilted by 45 degrees. This is a zoom in and this is a zoom out. And let's run the simulation and see what happens. So first thing that you see is that there are these low density polar regions. These are the jets. The disk is precessing, and so it's doing this sort of dance, which is just pure precession. But what you see here is that the inner disk has aligned with the black hole midplane. And there is a really rapid transition, really sharp, abrupt transition between the two, which is not something that we expected. So not only did we find the Barden-Peterson effect, this alignment near the black hole, but we also found that the disk can be broken because they cannot sustain this really sharp transition from the tilted disk to the aligned one, which can lead to really interesting observational manifestations, which we don't quite know what they are. This is an even weirder one. So this one is a disk tilted by 65 degrees, the same disk thickness. But what's going on here? The jets are kind of broken in their shape, as you can see. And the disk is not one, but kind of two. So let me show you how it looks like in 3D. So you see indeed that there is a disk that's broken up into two that are different by the orientation. And we will see what happens here from a movie. So initially the disk is tilted and the jets are perpendicular to it. But then the inner parts of the disk, they precess and they feel the pull of the black hole, precession pull of the black hole, and they cannot communicate it to the outer disk, and so they choose to tear off of it. And then the jets can smash into the outer disk and destroy it, which is what we've just seen here. And then the inner disk continues to break up into these smaller and smaller pieces. Eventually, we have 4 disks. The original one that was destroyed, this one, and the one at the center that just aligned. So we see Barton-Peterson effect over here. So this is really fascinating. This is not a standard disk that is like flat pancake with the jets perpendicular, flying perpendicular outwards from the disk. This is something else. There's a multiple disks with the jets trying to find the path of least resistance and make it out. The jets can collide with the disk, probably produce high energy emission, maybe accelerate protons, maybe produce neutrinos. So that's definitely something that we would like to understand here. Lots of physics to reveal, and even perhaps the most simplest one, what sort of observational signatures, what sort of photon signatures shall we get from here? We still don't quite know because here we didn't include radiation transport. We just cooled the disk to a given thickness, to target thickness, and we saw what happens. We are now on the precipice of running radiation simulations with radiation feedback, and that will allow us to compute radiative signatures of these disks. Okay, so far you see that there are jets everywhere, including here. Let's try to go here.
Sasha, can I ask a question?
Yeah,
Danny. But this effect of breaking the disk is really due to the frame dragging, you know?
Correct.
So it's something you would not get that in a neutron star. You cannot rotate that fast, no?
Correct. You wouldn't get it in the neutron star. Yeah.
Yeah. So and do you have some evidence that it's happening or not happening in a neutron star? Are there data that can tell you the difference?
Great question. I don't think we have the data in black holes to tell whether the disk is torn or broken. What we know is that in active galactic nuclei, the agreement between the standard, thin disk model and the observation is much worse than in the black hole X-ray binaries. It might be because of the different temperatures of the disk and therefore more complicated absorption cross-section. Or it could be due to the fact that many AGN disks are actually tilted, because we expect that in AGN generically the disk will be not aligned compared to black hole binary, which is whose kind of midplane is defined by the midplane of the orbit. So it's possible that we are already looking at these tilted disks in AGN. We just have no idea what we're looking at. And we have no idea how to interpret these observations properly. And so hopefully once we include the radiation, we will be able to compute radiative signatures of these jets slamming into the disks and disks being torn. We'll be able to compute the temperature profile. Do the disks become hotter towards the tear? And what sort of emission will we get? What sort of periodicity are we going to expect, because the disks are periodically precessing? Maybe that's where quasi-periodical oscillations are coming from. So I think we don't quite know answers to the very basic questions in the black hole case. With neutron stars, it just adds a whole extra layer of complexity. I think neutron stars don't get as much attention as they deserve. I'm not sure why that is. I think neutron stars provide a much more detailed window into the accretion flow than black holes, because you could time neutron stars so you know what torques the disk applies on the neutron star, and therefore you get an extra bit of information that can be used to test your models that in the black hole you simply don't have access to. And so neutron stars is definitely something that need to be studied theoretically through simulations and of course observations, and eventually hopefully we'll be able to get to the point where we will have a model that works well enough to match a lot of observational constraints, and that will allow us to improve not only neutron star models but also black hole models.
Okay, thank you. Mm-hmm.
So what about this? Maybe finally here we will be able to kill the jet. So this is a ridiculous model. The effective resolution here is 14,000 times 5,000 times 8,000 cells. Remember all the resolutions before? This is even crazier. Okay. Of course, this is not the uniform resolution. The resolution is focused within the plane of the accretion disk. Initially, it's a flat pancake that's tilted by 70 degrees, and the thickness of the disk is just 2%. This is the thinnest disk ever simulated in general relativity. The black hole spin is 93% of the maximum, so the rotational axis is vertical. So the black hole rotates like this, and the disk is tilted, so it rotates like that. So let's try and run the simulation and see what happens. Oh, and the left panel shows a 3D view, and the right panel shows the vertical slice. So you see that the frame dragging causes the disk to warp. That's how the disk comes to terms with the fact that the black hole pulls on the inner edge of the disk. And this warp sometimes is too much for the disk to bear, and so it tears off pieces near the black hole and they get consumed. And then a new piece gets torn off, and then that gets consumed as well. So that tear tends to happen periodically. And you will tell me, so what's the big deal? This simulation, very similar to the previous simulation, they look somewhat different. One thing that I didn't tell you is that this disk is with a toroidal field. So there is no field that's sticking out of the disk. The entire field that we started with was toroidal. And one very big difference is that there is no jets at all. Like you see, there is no empty funnel. There is no sign of the jets. And that's a first when there is no jet. What this means is that all of the effects that we're seeing here, the alignment of the inner disk, like you see here with the equatorial plane, the disk tearing and everything, this is not due to the jets, which some people suggested, because the jet can change the orientation of the disk, can cause it to align. Here, there is no jet, so there is no question that this alignment is happening because of the Barden-Peterson effect, as opposed to the interaction with the jet. And you can see how thin this disk is. And no matter how thin it is, we still have about 20 cells, if not more, per scale height of the disk to resolve the turbulence in it. And these periodic tears of the disk, they might allow us, if we understand what sets the size of these tears, to constrain black hole spin, for instance. Because if we know how large of a disk tears off from this bigger disk, then we will know what the precession frequency we're going to expect. And thereby, if we observe quasi-periodic oscillations from this precessing disk, and we know what the frequency of that is because we can measure it, we will be able to convert it into something physical, just like, black hole spin, for instance. But it's a long shot. We still need to work on understanding what exactly is happening here. So a grad student is working on creating a 1D model of this, where we'll take the turbulent properties from small scales, from the large scale simulation, feed them into this 1D model, and hopefully we'll be able to understand what causes the disk to tear, where it tears. And that would be amazing if it actually works. And these are the sort of the grid structures that we have to use, where they focus on the equatorial plane of the accretion disk to provide the resolution where it's needed. So now let me skip to the end over here, to my conclusions. Let's see, how does it work? Go to slide. Yeah. So here is the summary. The jets are everywhere. The only way to kill the jets that we found, short of smothering it with ambient medium, basically put a wall that the jets have no way of going around. If you don't have any external obstacles, the only way for the jets to disappear is to have a thin disk without any vertical magnetic field. That's the only way we found. These typical tilted disks, as I argued, they're typical. You always expect a tilt in almost any system, are extremely rich in exciting new physical effects. You have the alignment of the inner disk with the black hole midplane. The disk can break up into pieces. They can tear off and develop independently precessing disks. All of this is seen for the first time in general relativity with magnetic fields. And what's really exciting, we don't know what sort of observational manifestations we are to expect from this. So we are going to keep working on that. Really crazy and insane 3D resolutions now put us in a previously inaccessible plasmoid dominated reconnection regime of turbulence. And that brings us hope that we will finally be able to fully resolve the turbulence in accretion disks and not worry anymore whether our simulations are well resolved. And so now something that I didn't have a chance to talk about, but I can tell you in the discussion, we're now adding more physics into the simulations, such as radiation transport, which will allow us to actually make predictions, observational predictions for what these simulations will look like in the telescope. Thank you so much for your attention. Thank you so much for staying late.
Thank you, Sasha. Then we can start with the questions. Fabio, please.
Thank you for the presentation. I have one, maybe two questions about you showed in a plot the jet acceleration, velocity versus distance.
Yeah.
And I don't see, where are you? Oh, okay, yeah, okay.
I'm looking for that slide.
So
yeah, go ahead.
How can you extrapolate that figure to the GRB case? Because in that plot you had a velocity up to a Lorentz factor of 10. Do you have simulations in which you get much larger velocities with much larger Lorentz factors? And in that case, how is the acceleration as a function of the distance from the black hole?
Yeah, that's a really, really good question. So there are two factors that control the rate of acceleration and the terminal Lorentz factor. One factor is the shape of the jet. Basically, the jet needs to expand enough for the pressure gradients to push it out enough. That's factor one. And so for that, you need to have dynamical range because it takes time for the jet to expand. And that we actually have in the star because star gives you 6 orders of magnitude, whereas here we have 5. So GRBs and AGN are actually very similar in that respect. So what is this element that's missing in AGN that allows GRBs to accelerate so well? Well, the other factor is how strong is the magnetization of the jet at the base of the jet, meaning how dominant are the magnetic fields compared to the mass? Because if you have a spring and you put a really heavy weight on it, it won't be able to push it out. But if you have a spring and put a really tiny weight, it can shoot it out. So AGN jets are heavier, at least observationally, so it seems, because of the smaller Lorentz factors than GRB jets. So that is a difference, we think. For whatever reason, that's poorly understood, GRB jets do not entrain as much ambient gas as AGN jets do. I have some ideas of why this can be. We can discuss this, but these are just ideas. I don't have anything to back it up. And finally, GRBs have this extra way of accelerating. So let's say here we accelerate, as a power law, and we reach only 10. This power law can actually be steeper because it's limited by the magnetization over here in AGN, so it can get to higher Lorentz factors. But in AGN, you have ambient medium everywhere. In GRBs, once you get out of the star, you realize, if you or I am the jet, I realize that there is a lot of room for me to expand sideways. And so I will. And so it means that my radius will increase and the pressure gradient will emerge and push me out. So this sort of deconfinement acceleration can play a super important role. And so, yeah, you can easily boost your Lorentz factor by a factor of 10 like that. So you can, even if you get a Lorentz factor of 10 by the edge of the star, you can get 100 beyond for sure. In my idealized simulations, I found that the shape of the jets inside the star over 6 orders of magnitude can lead to acceleration of maybe a Lorentz factor of about 100. and then you can have another factor of 10 due to deconfinement acceleration at the surface of the star. I don't know if there is a limit to how much of a boost this deconfinement acceleration can give you. Maybe it can give you a factor of 100 in Lorentz factor as well. Basically, what happens is the jet opens up. That gives you an extra sideways velocity and also pushes you out. So these two components give you a higher Lorentz factor. Yeah, so that's what I think can cause the GRBs to move faster than AGN.
So also when the jet is inside the star, it can move with a velocity that can correspond to a Lorentz factor of 100. Are you saying? And when it breaks out,
yeah, right. So okay. So let me make a distinction here. While the jet is fully inside the star.
I mean
there is
the jet in the jet channel is moving with 100 from behind, and the shock wave is moving with a much smaller velocity, no? But the material
absolutely,
from
yes.
pushing with a very large Lorentz factor, or with a small Lorentz factor.
It can. So Lorentz factor can be very high behind the shock. Like when you inject hydrojets, you can inject them with 100 Lorentz factor, but that's not a problem for the shock. The shock doesn't care. You know, you have some ram pressure that comes out through a formula, you know, into which you put in the density of the jet and Lorentz factor of the jet, and then it flows back and kind of hugs the jet. And so that's how you get this jet cocoon structure with the shock that expands. Eventually, the shock reaches the surface of the star, and then the jet breaks out. The radius of the jet expands, the jet accelerates because the radius has expanded. And so then you have the other regime when the jet is open to infinity, that allows the magnetic fields to accelerate more because they're no longer bottled up by the shock that needs to drill through the star. And in this case, your Lorentz factor will go higher. And by the time the jet reaches the surface of the star, I wouldn't be surprised if it can be moving already at Lorentz factor of 100.
Thank you.
Enrique?
Any other questions?
Yes. So just hearing at this discussion made me forget my first question. Oh yeah,
no worries.
I remember. No, I remember now. So you had this plot or this space where you were plotting the how thick is the disk and how strong is the magnetic field. I was wondering if you had the third axis with the spin of the black hole, how much? So if you had a 0.1, would that also help remove the disk from your simulation? Because in the ones you showed, you had like 0.93. So if you had 0.1, 0.2, 0.3, would that also kill the jets?
Yeah, if you switch off the black hole rotation, there will be no relativistic jet. There will be subrelativistic winds, which are powered by the rotation of the disk. And why they will be subrelativistic? Because black holes are clean, like the vacuum cleaners. So if you have field lines that end up on the black hole, all the gas will drain off the magnetic field lines, and there will be very little gas for the field lines to accelerate. And so that's why they can accelerate to really large Lorentz factors, because they are light. And so therefore the magnetic spring has no problem. It's not loaded with a mass, it's not slowed down, can accelerate to large velocities. For the disk, that's no longer true. There is a lot of gas, and so the disk winds are necessarily going to be much slower. Now, if I switch off the black hole spin, you would say, that's another way of me killing the jets. And I agree with you. Yes, there will be no relativistic jets. The only problem is we know that black hole spin cannot be totally the answer in killing the jets, because in X-ray binaries, we have this thing called state transitions, right? Exactly, right. So we know that, an X-ray binary can go like over scale of a week or two through an outburst, produce, these powerful jets, and then shut off and produce no jet at all anymore. Of course, the black hole spin doesn't change in the scales of weeks or months or even, lifetimes, our lifetimes. So we know that it cannot be the black hole spin that is responsible for the production of the jets. Sorry, it cannot be a black hole spin of 0 that's responsible for jetless systems. It has to be something else. So there has to be a way for spinning black holes to produce no jets. Another perhaps less direct evidence, but still evidence, Chris Reynolds has a review on black hole spin recently. And if you look at the black hole spins in supermassive black holes, you will find that a lot of them have really high spins, but you don't get jets from many of these black holes. So what seems to happen is that if you have even if you have a rapidly spinning black hole, but it's surrounded by a pristine thin disk, like Shukuru-Synaev disk or Novikov-Thorne disk, the standard thin disk, you're not going to get a jet.
Right.
You're going to get a jet if you have a thick disk, sometimes, or if you have this weird transitional system where you go from a thick disk to a thin disk, like you haven't yet settled, which is what you get in the state transitions on black hole binaries. So my hunch is that you get jets everywhere except this pristine thin disk. And that's precisely what we're trying to get at, understanding how the transition from a thick disk to a thin disk happen, what happens to large scale magnetic flux, what happens to the structure of the accretion disk. Is it a single phase, a multi-phase structure? Is it two temperature with hot and cold phases? And probably because we see both black body emission from cold phase and power law emission from a hot phase. So all the elements are there. We just need to understand what is the geometry of them. Is it a sandwich geometry where you have a thin disk in the middle with corona above, or is it blobs of cold thin disk that are kind of floating, immersed in the soup of hot plasma or the corona? We don't quite know. And so we hope that when we simulate this radiation transport simulations with radiation on the fly treatment, we'll be able to finally tell what is the morphology of these transitional disks and what allows them to hold onto their magnetic fields. Most likely, it's because they just, basically you have a thick disk, the mass accretion rate goes up, the disk realizes, oh, for this high accretion rate, I can cool, so it collapses, but the magnetic field is still stuck in this disk. It will take it a while for the magnetic field to diffuse out. And so this is when you still make the jets. Eventually, the magnetic field leaks out, diffuses out, and then you get this pristine, thin Shukuru-Synaev disk without a jet, without large-scale magnetic fields. That's what I think is happening.
Okay, all right.
And hopefully we will show this through simulations.
Okay. Just a very quick question. So you had this jet which holds steady up to 10 to the 5 or something like that you were showing before. So at that stage, you no longer had a disk nor any pressure from the outside. So what's the morphology of the magnetic field inside the jet that allows it to stay stable? Or is it just that the material is already...
Sorry, I'm not quite...
So you were showing...
Are you asking about these jets?
Yes, yes. So the disk at that stage is no longer providing you with pressure on the outside. So something has to hold the jet together. So I'm wondering if that's the morphology of the magnetic field or what's helping you there.
Yeah, I think I might, if I figure out how to unhide this slide and yeah. Okay, so this is a vertical slice through the system.
Mm-hmm.
So this is 1500 gravitational radii. This is 0, so this is the equatorial plane. And this is about 500, minus 500, this is 500. Okay. So I'm going to play this movie. See if I can figure out how to play this movie. Yeah. So you see that the disk holds the magnetic field on the black hole. Later on, the outflows from the disk is what's holding the jet together. We call them the winds, and the disk should really be over there. And then you see that there are these instabilities between the jet and the wind, which may be the reason why AGN jets have so much mass, and that's why they're so slow.
Okay. All right. Thank you.
Sure, of course.
Well, it's 2 o'clock, so we'll finish here for today. Again, thank you very much, Sasha,
thank you so much, Rosa.
The wonderful talk. And for the rest, see you next week, and thanks for coming.
It's such a pleasure to see all of you. Thank you so much for inviting me. It was such a great pleasure. Have a wonderful rest of the day and the rest of the week.
Thank you.
Thank
Hope
you
to
very
see you
much.
around in person soon.
Bye.
Bye-bye,
See you.
everyone.
Thanks,
Bye.
Hassan.
Evening, Tom.
Thank
Thank you very
Thank
much.
you. Bye.
Bye bye.